Welcome to everyone. This activity is the result of a collaboration between Garrett Motion and POWERTECH Engineering, and it's about the numerical assessment of adaptive ECMS strategies for a gasoline hybrid electric vehicle on type approval and RDE driving cycles. This is the agenda of the presentation. After a brief introduction about the aim of the work, I will move to the case study chosen. I will then explain the reason behind the adoption of adaptive energy management strategy and the ones investigated in this work. I will then bring you to the results, and finally I will sum up my conclusions. The need to decarbonize transports and the need to reduce time and cost of the development process of electrified vehicles can be tackled by numerical simulation, which is the elective ground for the development of complex and innovative energy management strategy. The aim of this work is to develop an energy management system that adapts its operation in real time and that can guarantee charge-sustaining operation and optimal control on type approval and RDE driving cycles. Concerning the case study, for this work we choose a hybrid vehicle powered by a gasoline engine with 172 kilowatts and a 30 kilowatts electric motor, placed between the engine and the P2 transmission, the so-called P2 hybrid. The vehicle is a mid-size SUV featuring a 6-gears transmission. The entire vehicle is modeled in GT Suite with a map-based approach for the powertrain, the internal combustion engine and the electric motor, and an equivalent electric circuit represent the battery pack. The energy management controller of hybrid electric vehicles is based on a supervisory controller which defines hybrid electric vehicle mode or regenerative braking operations and the proper energy management strategy that determines the power split between the internal combustion engine and the electric motor. Among the various energy management strategies, the ECMS, the equivalent consumption minimization strategy, is chosen in this work because of its industrial appeal and ease of calibration. In the ECMS approach, instant by instant, this cost function, representative of the equivalent fuel consumption, is minimized. This cost function represents the sum of the engine fuel consumption and a fictitious virtual fuel consumption associated to the power coming from the battery, based on the assumption that the energy stored in the battery must be replenished using fuel energy. The parameter used to convert battery energy into fuel energy is the so-called equivalence factor K. In this work, a map-based power split optimization was used. An offline optimization tool was used to generate power split maps as a function of driver power, total power demand, driveline speed, and equivalence factor, taking into account e-motor, internal combustion engine, and battery limitations. The equivalence factor is the key of the ECMS. It is a synthetic value that is used to estimate the average chemical to electric conversion efficiency. It is a representative of past, present and future efficiency and affects charge sustainability and the effectiveness of the strategy. It is usually calibrated for a specific vehicle architecture and mission profile to guarantee charge sustaining operation. A fixed equivalent factor guarantees charge sustaining operation and close to optimal results in type approval tests, as seen, for example, on the NDC presented in the left figure. However, on long and high varying load mission profiles, the ones presented on the right of this slide, a single K may produce imbalance in the SOC profile, which is depicted in blue, jeopardizing the advantages of a hybrid architecture. In order to overcome these limits, different adaptive ECMS techniques are proposed. Concerning the main adoption techniques, in this slide I reported 3 most significant adaptive ECMS methods. you.